Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we'll continue talking about how we can use propositional logic to represent our knowledge base, and more importantly, how we can do inference over the knowledge base using the propositional logic. Last time we started to introduce or to refresh our minds with some of the basics of propositional logic. And here is the truth table for all the connectors or the operations that we mentioned last time: the negation, the and, the or, implication, and biconditional statement. Okay, and the most important one of them to remember is the implication statement, and you will see that P implies Q is true always, except in one case when P is true and Q is false. Remember that always. Okay. Now let's see how we can use propositional logic to represent the knowledge base. Okay, and our example, of course, is the Wumpus world. In the Wumpus world, we need to represent sentences that says that there is a pit or there is no pit in a specific room. Okay, so we can easily do that using a variable for each room that indicates whether there is a pit in that room or not. So for example, if we are sure that there is no pit in room 11, then let me change this to make it easy. Then we can say not P11. Not P11 means that there is no pit in room 11. And of course, we can have one like that for every room in which we know for sure there is a pit or not. Okay, so we should not say P3, 4, for example, if we don't know anything, if we didn't explore the room 3, 4, but if we didn't know for sure that there is or there is no pit there. Okay, we always add to the knowledge base things that are true, that are certain, that are sure. Okay, so that's of course an easy way to represent whether there's a pit or not. Also, we want a way to represent in the knowledge base the sensed values that we sense. Okay, so whenever we get into a room, we sense a breeze or we don't sense a breeze. Same with stench. So we need to add that to the data, to the knowledge base. So for example, not B11 means that we didn't sense a breeze in room 11. B21 means B capital, of course, B here means that we actually sensed the breeze in room 21, and so on. Okay, so whenever we get the sensed values, same with stench, of course, we should add the variable S with the subscripts that indicates which room we sensed the stench in. Okay, and so on. Same here, that if we want to add something about the Wumpus, we can say the Wumpus is in that room by indicating, for example, W23. So that means that we are sure that the Wumpus in room 23. Okay, so these are straightforward sentences that indicates whether there is a pit or Wumpus in room IJ, and also whether there is a we sensed breach or stench or anything like that in room IJ. We also need to represent the rules that we know about the game. For example, we know that if we have a breach, if we sense the breach in one room, then there is a pit in one of the neighboring rooms. Okay, how can we represent that? Easily by the variables that we already introduced here. So if you remember, we had this 4x4 cave. Okay, so this is 1, 2, 3, 4. This is 1, 2, 3, 4. Okay. Now, if we sense a breach in B11, so we sense the breach here, that means that we have a pit here, or we have a pit here, right? We cannot say that for sure we have a pit here, but we know for sure that there is a pit here or there, right? So if B11, then P12, which is this room, or P21, which is this one. Okay, with this notation, the row comes first here. Okay, Um, okay, and the other way also, and if we know that there is a pit here or there, then we have to sense a breach here. Okay, then we have to sense a breach here. Okay, so it's a biconditional statement. Breach 1 1 if and only if P12 or P21. Okay, same if we sense the breach in 2 1. Okay, so in 2 1, if we sense the breach here, then we can have a pit here or here or here, right? So it's P11 or P22, which is this one. This is 1 1. This is 2 2, or 3 1, which is this one. Okay, and so on. So we have to enumerate all the rules like that. Okay, whether for a breach or we can also say for stench and so on. Okay, so before even the beginning of the game, we should add these to the knowledge base, because that will represent the rules of the game. So not only what we sense is added to the knowledge base, not only what we entail will be added to the knowledge base, but also the rules of the game, or whatever we know that it is true, that is related, of course, to the game, is also added to the knowledge base. Okay. Also here, this is just an example. We should add all of what we get and all of what we sense also here. So that will be, as a whole, will be the sentences that we have in the knowledge base. And of course, as we move on, as we sense something, and we can, for example, we can, as we will see later, we can infer from something from these two. Okay, we have B21 and we have generally. Okay, generally you can infer something from these two. Once you have B21, then you know that it's P11 or P22 or P31. Now you can add this as a sentence to the knowledge base and so on. Okay, so that's generally how propositional logic will be used to represent sentences in the knowledge base. Any question about that? MashaAllah, we are 9 now. Any questions? Is everything clear here? Okay. Okay. Now, how can we infer something from the knowledge base? We have two ways, okay, that we will discuss, inshallah, in this lecture. The first one that we talked about already from the previous lecture, which is called model checking. Remember, if we say that the knowledge base entails alpha, that means we discussed two definitions for that. The first one is that whenever the knowledge base is 2, alpha has to be 2. Right? Whenever the knowledge base is 2, alpha is 2. We call the models in which the knowledge base is 2 the models of the knowledge base. So M of the knowledge base are the models of the knowledge base, or are the models where the knowledge base is 2. So in these models, alpha has to be 2, or that's the second definition, which is the models of the knowledge base has to be a subset of the models of alpha. Okay, now if we enumerate all the possible values for all variables that we have, and also the knowledge base, we can check this for any alpha. For example, if you look at this truth table, and of course you are familiar with this notion of truth table, we list all possible Boolean values for every variable. You can see that these 3 rows, in these 3 rows, the knowledge base is 2. Okay? Type. That means that these are 3 models in which the knowledge base is 2. What is a model? If you remember from last time, The model is an assignment of the variables, specific assignment to the variables. Okay, so each row here has an assignment for every variable. So each row here in that table is a model. But these 3 rows are the models of the knowledge base. Why is that? Because the knowledge base is true only in these 3 rows. Now, can we infer something from that? For example, we see that B21, this one, is always true here. Okay? Can we infer from that? Can we say that the knowledge base entails B21? Is that true? Can we say that? Any thoughts? Abdurrahman? You don't think so? Okay, what is the definition, Abdurrahman? Okay, what is the definition? What is the definition? When can we say that the knowledge base entails B21? Look at this. This is the definition, right? The models of the knowledge base has to be a subset of the models of alpha. Or you can say it in informal way, whenever the knowledge base is 2, alpha is 2. Is it the case here, Abdurrahman? Now we don't care. We don't care. That's the point. We don't care about any model in which the knowledge base is false. We only care here, to prove this, we only care about the models where the knowledge base is true, which is only these 3 rows. Okay? Exactly. That's exactly what we mean by entailment. Okay? The knowledge base entails alpha if whenever the knowledge base is true, alpha also is true. But we don't care. This definition doesn't tell us what happens to alpha if the knowledge base is false. We don't care. The example that you mentioned earlier, when the knowledge base is false here, B21 was true. We don't care about this. What we care about, in order to, if we are talking about this entailment, we care about models of the knowledge base and models of B21. Okay? If the models of the knowledge base is a subset of the models of B21, then we can say knowledge base entails B21. Now, where is the models of B21, Abdurrahman? Models of B21. These are the models of the knowledge base, right? Because of this, because we have only 2 here, only in these 3 rows. Where are the models of B21? Very good. So includes this one, includes these 3, and includes this one, and maybe some of the dots, right? We don't know. We don't see the dots, right? Type. Can we say that models of the knowledge base is a subset of the models of alpha, of B21? Yes. If that's the case, then this is true. Okay? Is it clear now, Abdurrahman? مفيش حاجة بالسهل يا عبد الرحمن. Okay. But it's really straightforward. Look at when we infer something, then we focus more on what we infer from. In the models of that, we look at the other one. So whenever, if we see that the knowledge base, whenever the knowledge base is true, another thing is true, then we can entail it. Let me give you another example. Thanks, Abdurrahman. Let me ask you about another thing. Can we say something about P21, this one? Can we say that the knowledge base entails P21? Faisal? Very good. Okay, so that's very clear, right? It's all false. طب how about Faisal also, stay with me. How about P22? Does not entail, yes, so we can just say this. So the knowledge base, again, okay, does not entail P22 and also does not entail P21. That doesn't mean that P21 is always is false, right? It doesn't mean that. It doesn't say anything about the value of P21 or P22. Thanks, Faisal. Now let me ask you another question. I think it's very clear that yes, the knowledge base entails B21 because everything is true here. It doesn't entail P21 and also doesn't entail P22. Now let me ask you about P21 again. Can we say something else about P21? Yani, can we entail something else about P21? Yani, we know that the knowledge base doesn't entail P21, but can we say something else, Abdurrahman? Yes? Okay. Type. Can we put it into an entailment statement? Aywa. Very good. Great. Thanks, Abdurrahman. So we can say that the knowledge base entails not P21. Very good. Okay. Why is that? Thanks, Abdurrahman. Why is that? Because by definition, okay, not P21 is true whenever the knowledge base is true. Right? B21 is always false whenever the knowledge base is true, which means not P21 is true whenever the knowledge base is true. Okay, so we can entail this. We cannot entail P21, but we can entail not P21. Okay? Is that clear to everyone? Any questions about that? Okay, very good. And it's also clear that we cannot do some similar things with P22 or P31 because some of them are false and some of them are true. So we cannot say anything about P31. Okay, so let me, if you don't have any questions, let me erase everything here. And this just says what we did. If the knowledge base is true in a row, then we have to check that alpha is also true in order to check if we can entail alpha or not. Faisal, you have a questions? Yes. Yes, you can have any expression here. As long as this expression is true whenever the knowledge base is true. Yani, yeah, you can put very complex expression here if you like. Okay, so alpha actually is not alpha is not, doesn't mean that alpha is just one variable. It can be, you know, that a Boolean variable can represent a very complex expression as long as it's Boolean eventually, right? So the definition holds with anything that is here. Okay, as long as it is true whenever the knowledge base is true, we can say that the knowledge base entails it. Okay, type. This is an algorithm to do something like what we did, but with enumeration. Okay, so in this algorithm, we enumerate everything and we check the models where the knowledge base is true, and we check whether alpha is true in these models or not. So this algorithm is called truth table entailment, and it takes the knowledge base and alpha and returns true if the knowledge base entails alpha, or false if the knowledge base doesn't entail alpha. Okay, and I will leave it to you to see it, but the core of it is depth first, something like depth first search that we did before. Okay, we actually go through all the rows in this table, given that we know all the variables. We go through all the rows, but in a specific order with depth first search order, or depth first order, and check the rows where the knowledge base is true, and for every row that the knowledge base is true, we check whether alpha is true or not. Okay, I will not go through it with you. You will do it on your own. The only thing that I want to emphasize here is that the time complexity, since this is enumerating everything, the time complexity is order 2 to the power n, is exponential. Why is it 2 to the power n? N here is the number of variables that we have. You know that the number of rows in a truth table, if we have n variables, the number of rows will be 2 to the power n, because we have 2 values for every one. So 2 times 2 times 2 n times, it's 2 to the power n. So the complexity, the time complexity is exponential. So this algorithm is very expensive. Although the space complexity is good, because we only keep n values of the variables, one value for each variable, but the time complexity is really big. It's very expensive, very costly. Okay, so we'll have to think about other efficient ways of doing inference. But this is a very brute force technique. Just enumerate everything and check if the models of alpha is a subset of the models of the knowledge base, which in other words, whenever the knowledge base is true, alpha is also true. To do that, we'll have to enumerate everything, and this is of course very expensive. Now we will switch to the second part of the lecture, which will be about an algorithm that is much more efficient than the model checking algorithm or the enumeration algorithm. This is called resolution. Let me share it with you now. I think you see the new slides now. Okay. Okay, so in the second part of the lecture, we'll talk about what we call the resolution algorithm. The resolution algorithm is an inference algorithm, which means that it will help us doing the entailment, okay, which is all about inference. Given the knowledge base that we know, how can we infer something new that is not explicitly mentioned in the knowledge base from what we have in the knowledge base. This is also called theorem proving, because if you think about it, we are also proving that if the knowledge base is true, then whatever we entail is true. So that's also a technique of proving theorems. Just a reminder of the logical equivalences or identities that we discussed, or not we here in this class, but that you studied in earlier courses like discrete math. You know that the AND operation is commutative, the OR operation is commutative. That means that A and B is equivalent to B and so alpha and beta is equivalent to beta and alpha, and so on. Associativity also holds in propositional logic, double negation elimination. Contraposition, this means, I think that's something that you need also to remember, that the implication statement can be written in a contraposition form. So if we have alpha implies beta, this is equivalent to not beta implies not alpha. Okay, so all of these rules can help us later, as we will see inshallah in this lecture, or maybe the next one. This is also very important to remember. That's how we convert from implication statement to OR statement. So alpha implies beta is equivalent to not alpha or beta. Okay, that's very important to remember. The biconditional statement, of course, is equivalent to two implication statements in both directions. These are the Morgan laws, and these are the laws for distribution of and over or statement, or over and statement. Okay, so these are all laws that you are already familiar with from discrete math. Any questions about this? Okay. Now let's talk about some new definitions. Some of them are new and some of them are not, and you will see how they are related to what we are concerned with here in this lecture. The first one is validity. Okay, a sentence is valid, we call it valid sentence, if it's true in all models. Okay, if it's true in all models. So for example, the sentence that is just true, it's of course true. A or not A is always true, right? Because and that's in all models, because any assignment of A will make this sentence true. Also, A implies A is true, and so on. Okay, so that's how we call a sentence valid. That means that it is true in all models. If you remember in propositional logic, that has another name. What was that name? A sentence or a proposition that is always true. How did we call this? And many of you actually took discrete math with me before, so you should remember. What is it? Anyone remembers the name? Okay. طيب. This was called tautology. Okay, that was called tautology. So a tautology is a proposition that is always true. That is always true. Okay. So but in this context we call it valid. So a valid sentence means a tautology. Now, how is that connected to inference? Here is how. The knowledge base entails alpha if and only if this sentence is valid. This sentence is knowledge base implies alpha. So that means that we can say that the knowledge base entails alpha if and only if the sentence knowledge base implies alpha is valid. Which means that if we proved that the knowledge base implies alpha using propositional logic, then we can infer alpha from the knowledge base. Okay, proving something means that it is always true, right? So if we prove that this sentence is valid, if we prove that this sentence is true, then alpha is entailed from the knowledge base, and vice versa, of course. If alpha is entailed from the knowledge base, then of course the knowledge base implies alpha is true. Okay, so it's working both ways, and that shows us one way of proving, or one way of inference, that if we can prove that the knowledge base implies some sentence, that means that we can entail that sentence, and now we can add that sentence to the knowledge base. Another definition, a sentence is satisfiable, and I think you are familiar with that already before. A sentence is satisfiable if it's true in some model. What do we mean by true in some model? There is an assignment to it that will make it true. So for example, A or B. Generally, there are some assignments of A and B that will make this sentence true. Like what? Of course, when A is true, then this sentence is always true. When B is true, then this sentence is true. That means that there is a way to satisfy this sentence, or there is a way to make this sentence true. That is satisfiability. Okay? In some model. So if we have at least one model, again, model here means assignment of values to the variables. If at least we have one model in which this sentence is true, that means that this sentence is satisfiable. If there is no model in which the sentence is satisfiable, then we call this sentence unsatisfiable. Okay? So the sentence is unsatisfiable if we cannot make it true. If there is no models that will make this sentence true. If there is no assignments to the variables that will make the sentence true. Like this sentence, A and not A. So A and not A is always false. Right? Because if A is true, then not A is false. If A is false, then A is false, then the whole sentence is false. So it's always false. Okay? So we call it unsatisfiable. We also had another name in propositional logic. Yes, Faisal, it is contradiction. This time you remembered it. Okay? It's contradiction. So this one is called tautology. It's always true. And this one is contradiction. That's always false or unsatisfiable. Now, how is that connected to inference? It's connected to a very important theory. Okay? The theory says that the knowledge base entails alpha if and only if this sentence is unsatisfiable. Okay? Which means the knowledge base and not alpha is always true. And if we showed that the knowledge base and not alpha is false, sorry, I said always true, I meant always false, sorry, okay, because it's unsatisfiable. So again, this says that if we show that the knowledge base and not alpha is unsatisfiable, which means it's always false, then we can entail alpha from the knowledge base. Now let's see why is that. Let's see why is that. If we say that knowledge base and not alpha is unsatisfiable, that means that it is false, right? Okay. Now, if we negate both sides, we can say that not. Can you mute the mic, please? Someone is not muted. Not. We can say not the knowledge base and not alpha is true. By De Morgan, we can say that this means knowledge base or alpha, sorry, not knowledge base or alpha is true. Remember what I said earlier when we talked about the equivalences, the identities, the laws of the propositional logic. What is that equivalent to? This is equivalent to knowledge base implies alpha. Okay, so knowledge base implies alpha is true. So if we showed that this is false, that means that this is true, which means that alpha is entailed from the knowledge base, as we said here. Okay, of course the implication here is double. Okay, is that clear? Any question about this? So this shows us actually one technique of inference from the knowledge base. If I have a knowledge base and I have a sentence that is that we want to check if we can entail from the knowledge base or not, we can prove that the knowledge base and not alpha is always false to show that alpha is entailed from the knowledge base. And you will see, inshallah, I think, hopefully this lecture, or for sure, inshallah, by the next lecture, you will see how this is useful. Okay, when we use the resolution algorithm, you will see that this is useful, and this is how actually we will make inference from the knowledge base. But both are equivalent, as we saw here. This one, it's the same as saying this one. Okay, and we showed that here. Okay, now let's talk about how we do inference in general, we earlier said that we have two ways. One of them we already covered, which is model checking. Okay, and that's that's what we do when we do the truth table enumeration that we did earlier in this lecture. As we said, this is exponential, and whenever something is exponential, that means that it's very expensive. That means that we should look for more efficient ways. There are some ways that will make this a bit more efficient, but still it is exponential, and we will not look at them in this course. What we will look at, inshallah, in this course is the other way of proving, or inference, which uses the inference rules from propositional logic to do the inference. Okay, and one of them is called the resolution algorithm, and that's what we will, inshallah, focus on in this lecture and the next lecture. But to use the resolution algorithm, which uses inference rules that we know about, we have to convert the sentences into what we call a normal form. So this type of proving methods require the transformation of sentences into normal form. And of course, the first thing to discuss now is what do we mean by normal form and how we will use it to do the inference. Okay, so that's the the outline from now, probably to the next lecture, inshallah. We'll focus on how we can use inference rules to do resolution, which is a method, an efficient method to do, or at least more efficient than the enumeration, to do inference. In order to do that, we have to transform the sentences that we have in the knowledge base into what we call normal form. So let's see what we mean by normal form first. The type of normal form that we will use in the resolution algorithm is called CNF, or conjunctive normal form. Conjunctive normal form, if you remember from propositional logic, this is what we call their product of sums. What do you mean by product of sums? Something like this. This is a product, because we have and here, of two things. Each one of these is a sum because we have or here. Okay? We call these literals. Okay? So these are literals, and the literals are either the variable or the negation of it. So not D is a literal, B is a literal, not C is a literal, and so on. So it's either the variable or its negation. Okay? Now, when we have or of multiple literals, we call that a clause. Okay? So this is a clause, and this is a clause, which is actually a sum. That's why we have sums here. Okay, so sum is a clause, but clause is, sum can be generally, it might not have literals, it might be more complicated, but a clause is just a disjunction of literals. Okay? Now, when we do conjunction of clauses, so these are the clauses. When we do conjunction, which is and of clauses, we get what we call conjunctive normal form, or in short, CNF. Okay? So that's the form that we need to have before we apply the resolution algorithm. Okay? Again, we have literals. Composing the literals through or operation will give us a clause. The and of the clauses is the CNF form. Okay, so that's the CNF. Now, what is the resolution inference rule? We will start to apply this rule. We start with two clauses. Okay, and let me show you the example first, and then we will generalize. Let's say that I have something like this, A, actually exactly this one, okay? So A or not B, that's a clause. And we also have another clause, which is B or not C or not D. In order to apply the resolution inference rule on two clauses, we have to identify a literal here in the first clause that is complemented in the other clause. What does that mean? We have in one of the clauses the literal and the negation of it in the other clause. Do we have something like that here? Yes, of course, we have not P, not B here, and we have B here. Okay, so this is the literal here that is negated or complemented in the other side. So that's the first step, is to identify one literal in the first clause that is negated in the other clause. Okay, once we do that, then we can infer from these two literals, from these two clauses, a new clause that will combine all of the rest of the literals in both clauses. So we can infer here A from the first clause, or, because that's the only remaining literal, after we cancel out this identified literal, which has the complemented form, complemented version in the other one, we cancel it out, and we list all the other literals. So A from here, not C, and not D from the other ones. All of them are, of course, OR. So that's another clause. So we infer this clause from these two. We will talk about why is that, and what is the meaning of the rule. We will show a sketch of the proof. Okay, but this is how it's implemented, how it's applied for now. Okay, we have two clauses. We have to identify one literal in the first one that is complemented in the other. If that's the case, if we have this, then we infer from these two clauses a new clause that lists all the other remaining literals after canceling the identified one. So we have A from here, and we have not C or not D from here. Sorry. Oops. Okay. So we infer this clause from these two clauses. What does that mean? That means that if I have in the knowledge base these two sentences, of course, having them in the knowledge base means that they are true. So this and that are true. I can infer from this a new clause, which is this. Okay, now let's look at the rule in general. First, do you have any question about this, about the application? Is it clear? Any question about how we applied it? Okay, so the general form of it is that we have two clauses here. Here from L1 to Lk and here from M1 to Mn. But we assume that Li, which is number I here, and Mj, which is number J here, are complementary literals. So we can infer from these two this one. So you see here that we have L1 to Lk, but we skipped Lj here. So there is no Lj here. Sorry, there is no Li, not Lj. Okay, because we assume that Li and Mj are complementary, so they should be cancelled out. So we should cancel Li from here and also cancel Mj from here. So Mj should be here, but Mj is not listed. Okay, and we of course connect them with OR. So that's the inference, the resolution inference rule. This is the resolution inference rule. Let's see another example. Okay, this one we have, we have P13 or P22, that's one clause, and another clause that's just not P22. Of course, here we can identify the complementary variable, which is P22. So we have P22 here, we have not P22 here, so we can cancel them and we can get out of them P13. Okay, now let's see this in a real scenario. In the not of course real, but in the Wumpus example, in the Wumpus world. Let's say that this of course has meaning in the Wumpus world. So P13 or P22, that means that we have a pit here. Let me. So that means that we have a pit here or a pit here. So this is the meaning of this clause. Okay, what is the meaning of this clause? That's not P22. That means that we know somehow that there is no pit in 22. So this is not true. Okay, of course we can infer from these two sentences. Yeah, this sentence says that there is a pit here or here. This sentence says that there is no pit here. That means that of course there is a pit here. Okay, so we can infer that P13 is true. Of course, looking at it as humans, it's very clear to us that inference is done automatically by our brain, but we have to automate it. If we want to have a system that does this inference, if we have an agent, if we want to build an agent that will do this inference, then we have to automate it. And the way to automate something like this is by the resolution inference rule. Okay, as we will see, we have to convert it, of course, into this form, which is CNF, and then we apply the inference rule, as we will see, inshallah, probably next lecture, because we don't have time now. Okay, so it might look very trivial to us, but we have to automate it. Okay, and this is one way of automating it. If we have these two, then we can infer P13. Now we can add P13 to the knowledge base. Now we can have P13 here, and maybe it can be used. So this two were used to infer this. Now maybe we can use this with something else to infer something new. Okay, and so on. So we can apply this resolution rule as many as we wish. Okay, to infer new sentences, and also as we move on in the world, we can get new sensed values. We add it to the knowledge base, and we infer more from the knowledge base. Okay, do you have any question about this, Faisal? Okay, which was this one? Yes. Yes. What do you mean by the same value? What do you mean by the end value? There is no end value here, Faisal. Okay, remember here, what is the context? It's good always to see the big picture. The context here is that we have a knowledge base. This knowledge base has sentences in it. Okay, and we got new sensed values. So we added this sentence, new sentence, for example. This is just an example. Okay, we added new sentence to the knowledge base. Now, can we infer something that we just added this sentence? Can we infer something from the knowledge base new so that we can also add it to the knowledge base and infer not something new and so on? So this is kind of learning, Faisal. It's not learning from data, but it's learning from what we from what we know plus what we sense. Okay, what input we can get. So from what we have, we infer something that was not explicitly written in the knowledge base. So from these two, these are kind of sentences, right? From these two, we infer this one. Exactly like here also, and maybe here it's more seen, more visualized. From these two, we infer this one. So there is no end value here. The thing that we want to know is how to get some new facts from the knowledge base and then act upon this. We didn't talk about the action yet, okay? But here we are focusing on how we can infer something from what we know already. Is that clear now, Faisal? Resolution can be seen as a simplification rule. We get something new from two existing clauses. If you want to call this process simplification, then it is simplification. Although, as you see here, the new sentence is not very simple, but it's at least simpler than having two clauses. Okay, but still you keep the previous ones because that's also something that is not that's needed. You cannot say خلاص احنا we will cancel these two and we keep this only. No, you add this to what you know already. Okay, because canceling this means that you don't know whether they are true or false. No, you should keep in the knowledge base whatever you know for sure it is true, because it will help you to infer something else in the future. Okay, is it clear now, Faisal? Okay, you're welcome. We'll have to stop here because we ran out of time. Inshallah, talk to you on Thursday. And remember, we will have the next quiz, inshallah, on Sunday. Okay, so the next quiz will be, inshallah, on Sunday, which is, I think, quiz 4. And it will cover everything, including the next lecture. Okay, it will cover everything, including the next lecture, inshallah. Okay, we'll stop here and talk to you on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.